This problem should look really familiar. This is not a mistake. We are going to solve the same problem that we did as we showed off how to use the kinematic equations, but now we're going to use it via the method of superposition. So it's the exact same problem, everything's going on. So let's take a look at what we are trying to do. So basically, what we have, free body diagram, I have my rod that's here. I've got my collar I'm pushing on with my 20 kilonewtons. And there is a small gap here at the end of 0.2 millimeters. And so the way that we're going to do this is we're going to make this up with our superposition. So the first thing we're going to do is we're going to say, okay, I've got this rod that I'm applying this load onto, and it's going to deflect. It's going to deform by some amount, delta P. Now I'm going to take that situation and I'm going to add to it this situation here where I just have this bar that I'm going to apply a force, FB, to push back on it. And actually, let's draw this a little bit differently. Let's draw this all the way out to the extreme stretch. I'm going to throw this force FB, and I'm going to push back on it till it goes back by some amount, FB. So I'm going to take this situation, add it to this situation. That's going to give me this final situation, which is the situation that we're trying to solve for. So if I look at that then, that tells me that whatever deflection I calculate from the load from the first situation minus whatever deflection I'm pushing back with is going to have to equal 0.2 millimeters, or 0.0002 meters. The reason for that is there's a gap there, and so we're going to be pushing back just enough to cover that gap. So what do? Well, we can directly solve for these just quickly. So the deflection of P, that first load, is PL over AE. So if I look at it, well, P is that load of 20,000 newtons, because now that we're ignoring that there's anything on the other side, it's statically determinate. We can just go, okay, well, that's 20 e to the 3 newtons. The length over which it acts. Now, if we go back and we look at this picture, once we remove any reaction here, that 20,000 newtons is only working along that part of the bar. Because if I cut it here, and if I do a free body diagram of that here, so I'm looking, I will have 20 kilonewtons here. If I do an overall free body diagram and it's not touching, well, that tells me the reaction force has to be 20 kilonewtons. That balances out. So any internal force here would be 0 kilonewtons because it's completely balanced out by the reaction force. And that's if we're ignoring that there's a wall at B. So as I'm looking at that 20,000 kilonewtons that 20,000 newtons operates over only that first 0.4 meters, because after that it's nothing. And then we have our area, pi over 4. I'm going to convert my millimeters into meters, so d squared times 200 e to the 9th newtons per meter squared. And so what that tells me is the deflection due to that load when that wall's not there is going to be 0.509 times 10 to the negative 3 meters. Okay, and so now I calculate out my deflection of B. And B is going to be PL over AE again. So B is going to be that force at B. Now the length, this time, what I'm doing is I'm removing that initial force because I'm trying to figure out how much force I need to push the whole thing back. So I'm doing this situation right here. And so I just have FB pushing back on that. There's going to be no other forces on it aside from FB. But FB is also acting over the entire length of this, because no matter where you cut it, you take a look at the internal force, it's going to be the same as FB. So now we've got that's operating over the entire thing of 1.2 meters. And then we'll divide that by pi over 4. The same thing, just the area again times the modulus of elasticity. And so now that I find, okay, well that thing's going to deflect 76.3944 times 10 to the negative 9 meters times FB. Okay, so now what do we do? Well, I know that the deflection of the first force minus the deflection of us pushing back has to equal 0.0002 meters. Sometimes this would be 0 if it was tucked into the gap, but the bar is allowed to grow by 0.2 millimeters, so we have to take that into account. And so we can just sit here and we can plug that number in, because I know there's my load deflection from the initial load. There is my load deflection from B. One equation, one unknown. So I sit there and just substitute all this in. 509 e to the negative 3 meters minus 76.3944 times 10 to the negative 9 meters times that force of B is equal to 0.02, forgot a 0, 2 meters. And so now if I go and I solve this for the force of B, what I'll get is 4.05 kilonewtons of force. So that's what the reaction is going to have to be at B. Now, one thing that we did not do with this one is initially we did not draw our very first equation that shows it was statically indeterminate. We had that from the other one, but I really should have drawn it out here. So the sum of the force in the x direction are going to be 0. And so if I draw a free body diagram of that entire thing, let's clean up some. So if we assume this thing grows out to hits point B, then I will have a reaction of A. I will have my load applied. I will have a reaction at B. And we really should have done this to begin with, because this would have shown us it's statically indeterminate. I just got really excited and wanted to jump in and solve the problem. So negative RA minus RB plus P is going to be equal to 0. So that means P is going to be equal to RA plus RB. So if I come down here, P is 20,000 kilonewtons is equal to RA plus RB. We can now plug RB into our equation here, and you're basically going to get that the force in A. Yes, and I know I have a bad habit. I'm used to all of my reaction forces labeling R, but the book that we use, especially in the examples and whatnot, uses F, and sometimes I mess up. So I do apologize about that. So we plug FB into here. We can turn around and calculate it out FA, and so that means that FA is 15.95 kilonewtons, or basically 16 kilonewtons. And then if you go and look, that's pretty much the same answers that we got using the kinematic equations. So it really doesn't matter if you go method of superposition or kinematic equations, you're going to get to the same answers. It's just all what's better for you and how you want to do it. I will not direct you to, hey, solve this with kinematic equations, or hey, solve this with superposition. I will just tell you, hey, solve this statically indeterminate problem.